of the low as far as statistics are concerned. But that's a reasonable way to think about it. You should realize that that's not correct. The correct interpretation is if we did lots of samples, which we don't, then 95% of those samples, of the intervals computed from those samples, would contain the true median. Question?
When we calculate the bootstrap median confidence interval for the median, does it matter how many times we are repeating?
Well, yeah. Okay, so here's what people don't like about the bootstrap is the fact that if all of you compute, if we have data, I take the data, the 50 data points that I have, and you all compute bootstrap confidence intervals, you're all going to get different answers. People hate that. They go, that sucks. Everybody's getting a different, well, what's the right answer for the confidence interval? Guess what? They're all right. And so no one likes that. And I said 1,000. Why did I say 1,000? Because 1,000 kind of works pretty well. I can simulate it and go, oh, look, works pretty well. Is 10,000 better? Sure. More is always better in statistical terms. So should I do 10? There's some law of diminishing returns that, yes, it's true, I'll get more, and if you all go out and do 10,000 each, your confidence intervals are going to be closer to each other. They're still going to be different. They're all right. In some sense, it doesn't matter which one we use, because they're all about the same. They're all going to come out about the same, but not exactly the same. And so, no matter what, if we use normal theory to make the confidence interval, we're all going to get the same answer. People like that. They don't like the fact that the answer is different every time you do it. On the other hand, this confidence interval is way better than having to assume that you know the distribution of something that you don't know the distribution of. It's not as good. So I generated that from an exponential distribution. That exponential distribution has a formula. If I put that formula in here, this confidence interval is going to be better than that one. And it's fixed. Everyone will get the same answer. Except in practice, you don't know. You can't know that your data came from an exponential distribution unless you randomly generated it. And so this should have parentheses around it. The resampled confidence interval is often used in cases where we haven't done the theory. That happens all the time. Or the theory suggests something that is not easily estimated. So that's the game that's played in resampling. So when someone says they bootstrapped it, that means they sampled from, so in general, if they say they bootstrapped it, they resampled from the data set. If they don't say it's a sample size of size n with replacement, they computed all these guys, then they did something with them. You don't have to use the percentile method. You can also base it on the standard deviation of these things. Turns out the standard deviation of these things is an estimate of this standard error right here. Is that better than, so alternative is the, I don't know what to call it. Not the, that's a percentile. It's the standard error estimate. bootstrap confidence interval. Basically, the standard deviation of the m hats i's estimates the standard error of m hat, this thing over here. This, some people like this one because it generates a symmetric confidence interval. But this is not symmetric. So, because the distribution is skewed, so if you go out in this direction, you're going to go out further in the tail than in this direction, which is going back towards 0, and you're going to end up with what's called an asymmetric confidence interval. And people don't like that. It's supposed to be something plus or minus something, and that's not what happens with the percentile confidence interval. The percentile one is actually better, but that doesn't mean that you won't see the median plus or minus something where there's a note that says this is a bootstrap confidence interval. So now let's talk about the jackknife. The jackknife actually came before the bootstrap. I have to remember that I have a meeting at noon. So this is a jackknife. Now, jackknife confidence interval or jackknife variance estimate is different than a bootstrap. In this case, we're going to make resampled. We're going to resample, but we're going to resample in a different way. And this is going to be, it's called the delete one jackknife. Instead of resampling with a replacement to get variability in these m hats over here, we're just going to pull one of the observations out of the data set. Remove observations one at a time and compute your statistic. So this notation is m sub minus 1 without the parents, m minus 1, m minus 2, dot, 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 m minus n. So you just take one observation out and recompute whatever your statistic is. In this case, our statistic is the sample median, so you just recompute the sample median for all the subsets of the data with one observation deleted. And so then make a confidence interval. Out of these things, you can do the percentile method, you can do the standard error method with the jackknife. And the jackknife has this super cool property that everybody gets the same answer. Because there's no random sampling, the advantage. Everyone gets the same answer. And that's great. Except the jackknife fails for the median. Disadvantage. It doesn't work for the median. It does work in lots of cases, but it doesn't work for the simple case of the median. The reason it doesn't work is it doesn't create enough variability. When you delete one observation, your median shifted downward a little bit. If you deleted an observation above the median. You deleted an observation below the median, your median shifted up a little bit. So there's almost no variability in these medians. And that makes the jackknife confidence intervals fail. So when Brad Efron was thinking about this problem, he came up with the bootstrap. Let's do something different than what the jackknife does. Instead, we'll sample with replacement. That'll make more variability. So you can, if you just think about these guys, they're going to be more variable than these guys. And it turns out that there isn't enough variability in the